Yeah. Okay, so we're ready for the next talk. Our presenters are Ondřej Metelka and Petr Sojka, and they're going to be talking about UTFpatgen.
Hello everyone and warm welcome from Brno. My name is Ondřej Metelka and today I will be presenting on my behalf and on behalf of my co-author Petr Sojka about UTFpatgen, hyphenation without borders. Let me start with a brief overview of the presentation. The first thing will be an introduction where I will talk about the context of the article. Then I will move to motivation part. The third part is about the UTFpatgen itself, where I will talk about the implementation, the improvements we did, and the integration into the landscape. Then we will move to the evaluation part, where we will introduce the experiment and the results we observed. And finally, there will be a conclusion part where I will summarize the outcomes of the article. Hyphenation is a technique used in typography to split words at the ends of lines. The editors use it to achieve nicer layout of the text with block-like alignment or consistent spacing. It becomes even more relevant in paragraphs that are really tight, such occur in smartphone screens, for instance. Hyphenation software is embedded also in text editors or web browsers. The most widely used approach to the word hyphenation problem is through hyphenation patterns. These can be generated from dictionaries by the PatGen program. And the example below shows an entry from such hyphenation dictionary. This one is Merriam-Webster. And the hyphenation itself can be seen as the first thing on the second line. Few words about PatGen, which I mentioned on the slide before. PatGen stands as an abbreviation for Pattern Generation Program. The first version comes already from 1983. However, there were some updates, and the latest version 2.4 is from 2020. It is written in web literate programming language, which is a combination of the Pascal programming language and plaintext documentation. The core idea of PatGen's algorithm is to iteratively loop through the input dictionary and to collect candidate patterns. These patterns are then evaluated with their frequencies and the user-specified acceptance criteria. The program uses mixed command line-based and file-based approach. That means all inputs and outputs are specified through files, and additionally, the program prompts for numeric parameters at runtime. Here you can see a high-level scheme of the algorithm. In the bottom left corner, there are 3 input files: the dictionary, which contains the hyphenated words, the pattern file, where an initial set of hyphenation patterns can be specified, and the translate file, which contains a character mapping. That means the lowercase and uppercase characters. The output file in the top left corner is also provided to PatGen, but it is used as an output parameter for storing the generated patterns. We can divide the execution into 3 phases. In the preparation phase, the initial patterns are parsed, the character mapping from translate file is parsed, and the user specifies the range of hyphenation levels. The pattern generation phase contains the dictionary loop itself. The user provides the range of pattern lengths and the acceptance weights. These are used to evaluate the candidate patterns and select those that will be part of the persistent set. This is repeated until all the levels were processed. The output phase then writes all the persistent patterns into the output file. The user may specify that they want to hyphenate the dictionary as well. In that case, another file called patgen is created, and this contains the hyphenated dictionary. Although the algorithm is quite efficient, there are several technical limitations that make the pattern generation impossible in some cases. Firstly, PatGen posts hard bounds on the input dictionary. First and foremost, it allows only a certain number of lowercase characters to occur in the dictionary, and additionally, it limits the word length to 50. The processing capabilities are limited as well, with only 9 hyphenation levels and patterns to the length of at most 15 to be generated. And lastly, there is some technical debt, which stems from the age of the program. For instance, the modularity is quite low, which makes the maintainability and testability even lower. As a consequence, PatGen is practically unusable for some use cases. Firstly, when processing data from the web, there is a chance that we will encounter more distinct characters than PatGen allows. With larger input alphabets, we would be able to explore the field of universal patterns. This means joining several languages into one set of patterns and consequently saving some space. Secondly, we run into problems when the hyphenation dictionary contains words that are too long. This can happen, for instance, in German, which uses compounds quite often. With these issues in mind, we started working on a new hyphenation program that we call UTFpatgen. We chose the CWEB language for implementation. CWEB is a successor to WEB, which still follows the literate programming paradigm, but switches Pascal for C. The reason is that C offers few features that we find useful, for instance, the dynamic memory allocation. We managed to implement the algorithm almost identically to PatGen with just 3 exceptions. Firstly, we changed the character mapping so that the alphabet size is increased. Then we adjusted the weights and levels representation so that the scope of these parameters is increased as well. Finally, as mentioned before, we use dynamic memory management so that the static structure sizes of PatGen are no longer an issue. We also perform several general refactoring tasks, such as variable localization, grouping of related variables, function decomposition, and we eliminated the go-to statements which are deemed harmful. Let me now talk about the character mapping, which was the biggest adjustment we did to the PatGen algorithm. We faced the challenge that the algorithm was designed to work with just single byte characters, which would leave us with only 256 distinct characters in the input alphabet. So we proposed a method that translates each character into a uniquely decodable sequence of bytes. It is a two-step procedure. Firstly, we assign each character a unique index from 1 to n, and then we convert the indices into sequences. You can see an example mapping in the figure on the right. We start by assigning only single-level sequences and add another byte only when the smaller ranges is fully exhausted. Thanks to this trick, we keep the mapping compact and memory efficient. We can also easily distinguish the sequence boundaries so that we are able to process only those positions that correspond to places between original characters. We draw inspiration from the UTF-8 character encoding, which also uses variable byte length, hence the name UTFpatgen. To achieve even bigger space efficiency, we can sort the characters in the translate file by their frequencies in the dictionary, so that the most frequent ones get the shortest sequences. This slide shows the compilation process of the program. The CWEB language allows us to generate not only the binary itself, but also a PDF report that contains the formatted documentation sections. Both targets require utilities from the TUG distribution. ctangle extracts the C-source code from the CWEB file, and CWeave transforms the file into a plain text document. From those points, the compilation is standard for the respective languages. Here, we summarize the improvements of our implementation over PatGen. In several aspects, we removed the bounds completely, see alphabet size, input word length, and input letter size, while in others, such as hyphenation levels, weights, and pattern length, we increased the scope significantly. Newly, the user does not need to reconfigure the structure sizes if their application does not fit the default setting. This is done dynamically at runtime. We also dropped the platform dependency in the case of acceptance weights. Although it may mean that the value range is smaller now, it is still sufficient in our opinion. We strived for maximal interface compatibility with PatGen. Besides the hyphenation level and weights representation, the two programs are completely interchangeable, and even this difference can be solved by a simple command line translation. UTFpatgen will appear in the TUG distribution next year, and the source code repository is already published under the MIT license on CTAN and GitHub. Now, the presentation moves to the evaluation part. We ran UTFpatgen with several configurations and observed its behavior compared to PatGen. As the base for experimentation, we created the hyphenation collection of hyphenation dictionaries. Hyphenation comprises 18 datasets in total from 15 languages, including non-Latin scripted languages such as Russian and Ukrainian, which use the Cyrillic alphabet, Modern Greek, and Thai. The data come from various sources of different quality. The collection contains datasets created by scraping Wiktionary, as well as polished academic dictionaries. The benchmark also comes with multiple parameter profiles. These are configurations of input parameters, such as the number of levels, the pattern length, and the acceptance weight. The variables we observed fall into two categories. The correctness variables check the algorithm outputs against the outputs of PatGen, and the performance variables compare the two programs in terms of execution time and memory consumption. The results were rather satisfying. The test did not exploit any discrepancies between the implementations, and we were able to process a joint Hyphenation dictionary with over 300 characters. The performance measures dropped as expected, but the relative change was acceptable. Both execution times and consumed memory exhibited less than 3 times worse over PatGen, which we deem an okay trade-off for UTF-Patgen's flexibility. It is important to note that the parameter profiles played an important role in the observed ratios as well. This final slide concludes the presentation. We introduced UTF-Patgen, a program for hyphenation without borders. UTF-Patgen extends the original PatGen program in several ways. Thanks to improved character mapping, we are able to process dictionaries with arbitrarily sized alphabets. Further adjustments to the memory management and parameter representation allowed us to increase the flexibility of the program. And lastly, our implementation underwent a refactoring phase for better testability and maintainability. We evaluated UTF-Patgen on the hyphenation collection of hyphenation datasets. We did not find any algorithm flaws and observed only a modest performance drop compared to PatGen. The integration into the open source landscape is ongoing, with the source code repository freely accessible, and the program waiting for inclusion in TUG 2027. And that was all from me. Thanks for listening, and have a nice rest of the conference.
Well, thanks so much for this nice talk. Oh, the microphone's working again, I guess. This a microphone with artificial intelligence. Who would have believed it? It decides that I'm okay now. Thanks so much for that fine talk. We have a few moments for questions if we have any from the audience.
Since you are accepting I'm Marcel Krüger. Since you are accepting Unicode input, what is your definition of a character in your character splitting?
Do you mean character in the input text?
Yes.
As it's mentioned, it can be an Unicode character, and if I'm not mistaken, it should be just UTF-8 encoded character.
So a Unicode
Yes.
code point, basically.
Yes.
Yeah.
Yes, it is. Similarly, as ZTech accepts UTF-8 input, UTFpatgen accepts any UTF-8 character.
Did you consider how it would affect the pattern generation if instead of looking at Unicode code points, you would look at grapheme clusters to avoid having these separate characters for combining
It
stuff?
seems that Max is speaking, but we do not hear anything.
Oh, I did hear the question, but could you please repeat it once more?
Sure. I was wondering how pattern generation would change if instead of Unicode code points, grapheme clusters would be considered as input units.
What was the thing that should be instead of UTF-8?
Unicode grapheme clusters, so that you combining characters.
I'm not so proficient in how this works on the byte level, but I guess as long as these clusters are not hyphenated anywhere in the data, like there is no hyphen between those three parts or two parts of the character, then it should work fine. Or it will treat them as two characters or three characters or whatever the number is.
Okay, any further questions?
Is Peter muted?
Yes, that's what I was going to
I
Hello?
This is
You hear
Barbara
me?
Beaton. The problem that I've found particularly annoying is this.
I don't hear Max.
Just hold that one.
Sorry about that.
try now.
A problem that I've found particularly annoying is the fact that compound words from chemistry and other medical terms, there are proper hyphenations or allowable hyphenations in many places, but the preferred ones are between the compounds. And it's impossible with the original PatGen to distinguish between them. Is this something that can be handled with the improved PatGen?
You can somehow assign weights to hyphenation points that you want to prefer. So in a sense, that should be possible. But I think it's possible also in the old PatGen.
Yes.
Maybe just the range of weights is smaller.
I haven't found a way to distinguish the weighting of the different hyphenation points.
Yes, one cannot by now, but as with increased number of levels, you may have patterns that in LaTeX distinguishes between results achieved by levels 1 to 4 or levels up to 16, let's say, and this way you may have in one pattern set different hyphenation points encoded, and that's due to the increased number of levels. And similar technique might be now used for multi-language patterns and other obscure ways how to encode language information for words in patterns.
Is that good, or do you want me to?
I'll be in touch. Thank you.
Wow,
That's
sorry,
actually
I
a
do not
pleasure, not a
hear
threat.
anything now.
Are there further questions? Nope.
Sorry about
You have
that.
to be loud voice, I'm afraid, Charles.
Hi, Charles Statz. You mentioned that the UTFpatgen has slightly lower performance than the original, and
I don't hear anything now.
I can hear clearly, so maybe
Okay.
I can answer the question.
Okay, so anyway, I mean, from a practical matter, I'm guessing that's totally the performance difference is pretty much irrelevant. But I am curious: is the difference just an expected result of using a more complex setup, or having more options that take up more space, or is it is it a result of the older one having been around longer and been subject to more optimization?
My opinion is that, for instance, the dynamic memory management may cause a bit of slowdown, as opposed to the static sizes, which are just really easy to compile and optimize by the compilers. But yeah, there might be some super optimizations in the old code as well. Yep, you're welcome.
Are there any other questions? Besides, will this microphone work? Okay, we seem to be good. So let's thank our speakers again. It was really very pleasant.
Thank you.
Thanks.
Nice to see you again, Peter. That's it. Okay, so we'll be resuming at the top of the hour, so you have just a couple of minutes to chat.